All good. Hello, everyone. This presentation is divided in two parts. So my part is meant to introduce a new project on aquifer and groundwater characterization in southern Ontario, and more specifically in the western part of the Niagara Peninsula. And Denis will talk about a specific scientific aspect of the project, so it'll be more interesting. I just would like to say that this project was launched in April, and it was in response to a request from the Six Nations community to the federal government for assistance in addressing the poor quality of groundwater on the reserve. So, the study area corresponds to the lower part of the Grand River watershed, so it's about 2,000 square kilometers. It's delineated in red, with two First Nations reserves in the middle, Six Nations, which is the largest reserve in Canada, and Mississaugas of the New Credit, or the Credit, they changed the name of the Credit, which is just next to it. The study area is much larger than the two First Nations reserves in order to understand properly the context and the various water quality issues. These issues, in general, north of Lake Erie, are known to be caused both by natural sources and anthropogenic activities, including salts from the Salina group, de-icing salts, malfunctioning septic systems, nutrients from agriculture, and leaks from a number of legacy oil and gas wells, because many of them were abandoned with the methods employed at the time. So all these issues pose serious problems because some parts of the aquifers contain groundwater that is brackish, gas-rich, or contains other compounds, making sometimes groundwater unfit for consumption. Another serious problem is the presence of H2S, as Tassiani described in her presentation. It's a toxic gas, because as methane escaping from deep hydrocarbon reservoirs passes or migrates to the surface, it passes through the Salina group, likely causing sulfate reduction and the formation of H2S. And Denis will talk about that after. As you probably all know, the study area in this region in general is very agricultural, and a lot of people use groundwater for their water supply. As I mentioned, and as Tassiani presented, there are a quite large number of oil and gas wells in this area. Only within the study area, most oil and gas wells are located in the northwestern part, and especially in the southeastern part, and only in the Six Nations reserve there are, that we know, about 250 of these wells, and it's only over less than 200 square kilometers. This is a map showing the shallow bedrock units with the Salina group that contains evaporites shown in yellow, and most of the oil and gas wells have been drilled south of the northern limit of the Salina group, because this unit forms a regional seal that retains hydrocarbons below it. So it's mostly natural gas or methane, if you want, in this area. The objectives of this project are first to understand groundwater flow in the study area. This involves characterizing the properties of shallow aquifers and integrating the knowledge gained in 2D and 3D coupled numerical models, and eventually including predictive models, notably for climate change scenarios. And the second objective is to study the impact of natural and anthropogenic contaminants on the region's water resources. And this involves characterizing the quality of surface water and groundwater in combination with air and soil measurements to better define or identify the various sources of contaminants. as part of this second objective, a study of the history of the landscape and environmental changes over the past few decades and the impacts on culture, health, and lifestyle is being conducted based on interviews and discussions with members of the two First Nations communities. And if you were there this morning, you heard Rohini and Dawn talk about this study because they're in charge. Among the data available to help us understand the hydrogeological and hydrogeochemical context, and of course, in addition to the existing geological maps and models, are data on water wells, mainly from provincial databases. On this map, active water supply wells are shown in blue and abandoned water wells in red. It may not be obvious on this map, but there are quite a few abandoned wells, certainly for a variety of reasons, including the poor quality of, or the lack of good quality data. Fortunately for us, there are several provincial monitoring wells and wells for which geochemical results are available, thanks to Stu Hamilton and now Laura Colgrove of the OGS for this work. This geochemical database is amazing and will be extremely useful to this project. Same for surface water quality data. They will be very important for this study. Just to say that this project involves a lot of people from the federal government, from 3 provincial ministries, from 4 universities, a consulting firm, the Hydrogeospheres developers, and 2 First Nations communities. As I said earlier, this project started a few months ago, and I've been pretty busy with administrative tasks, but I'm not alone, so we were able to hire 2 PhD students, so that's great news. There's one that is currently at the University of Guelph that will work on hydrodynamics, and the second will be at INRS, so in Quebec City, and will work on geochemistry. We're in the process of hiring a technician, and hopefully this person will be able to begin in a few months because we were able to secure funding for the drilling of a few monitoring wells, and hopefully they will take place in August. We gave 2 contracts, one to Six Nations Polytechnique and one to Matrix Solutions. And I also would like to say that we've been working on a Six Nations Ethics Committee form because in order to work with Six Nations, we need to fill out this form that contains a lot of questions to make sure that they understand what we are planning to do and that we are respectful. And for this, they have a specific section in this form that is about OCAP principles. I don't know if you are familiar with these, but these are principles that we must respect when conducting a scientific study or research study with First Nations communities. And OCAP stands for ownership, control, access, and possession. So it's really about data and results and how we deal with them. And let's just say that the federal government was not ready for that. I filled out this form last summer, and since then, I've been dealing with the Intellectual Property Division, Legal Service, and Nokwe Wash, that is our liaison service with Indigenous communities. There have been many versions or iterations, call it as you want. And but last Friday, we came up with an almost final version that we will present to the community. And lastly, we developed a project flyer. That sounds really simple, right? No, not at the federal government, because everything that goes out to the public needs to comply with a lot of rules. So again, many iterations and compromises. Anyway, so I'll leave it there, and I'll let Denis talk about more exciting things. Thank you.
Thanks, Christine. My part is, okay, we're okay. I will be presenting some facts and ideas about the H2S issue in groundwater, which was previously nicely covered in the previous presentation. My aspect or my part in this job was initially to distinguish between various sources of sulfate, rocks of mineral sulfate, that are possibly involved in the formation of H2S. H2S can be formed by various processes. One of the most common processes is the reduction of, sulfate reduction. Sulfate reduction can proceed by two main mechanisms. First is a low temperature process involving microbial activities, which operates at temperature below 80 degrees Celsius, roughly. And the other process is through thermochemical sulfate reduction by high temperature. In southern Ontario, these high temperatures were not reached by the units. So what we are dealing here most likely is a microbial sulfate reduction. So what you need is a source of methane and sulfate, mineral sulfate. Those two cannot coexist in nature. They will immediately or very rapidly react in solution to form H2S. In southern Ontario, we have two potential sources of calcium sulfate, main sources of calcium sulfate, which are gypsum, which is an hydrated calcium sulfate, and anhydrite, which is the same calcium sulfate but without water. So the project was initially try to distinguish between these two types of sulfates and see if we can pinpoint a mineral responsible for the formation of H2S. So here what we have to the left, is the simplified geological map of southern Ontario. The area in southern Ontario is divided in two main geological domains. We have to the northwest, the Michigan Intracritic Basin, and to the southeast, we have the Appalachian Foreland Basin. Those two basins are of similar age and are separated by tectonic height known as the Algonquin and the, which are here, the Algonquin and the Finlay Arches, which is the tectonic high. Even though we have two separate depositional basins, they share a similar stratigraphy, succession of rocks, which range in age from Cambrian all the way to Mississippian, and it's mostly dominated by various carbonates, shown in blue on the slide here to the right. Carbonates including limestones and dollostones. You have some subordinate amount of classic, including coarse and fine-grained classics, and the fine-grained classics are locally rich in organic matter, and they are an excellent methane source rock, hydrocarbon source rock in the basin. So this here, we see the location of the study area in gray, the Grand River watershed. So it's located in the Appalachian Foreland Basin. And from 1 to 8 are 8 wells that we studied, we sampled for the anhydrite, which is present in the deep subsurface in that area. I forgot to mention that in the middle part of the succession, we do have in upper Silurian succession known as the Salina group, which is rich in sulfate. This is the unit that has the most volume, the biggest amount of sulfate in the subsurface. So sulfate in the deep wells, deep exploration wells in that south and southwestern part of the basin consists of anhydrite. So we have sampled some of these wells for their anhydrite content. Now moving into the area of interest, which is the Grand River watershed. This map is from Abigail Burt work in this area. And we have sampled a number of wells, 8 wells, for the Salina group in this area, and the Salina here consists of gypsum. So we have this suite of samples consisting either of gypsum in the local area of interest and deeper anhydrite in the deeper oil and gas exploration wells. So the idea was to contrast these two minerals and see which one might be involved, preferably in the formation of H2S. So this is first the core, how these sulfates looks in core. Sulfates are minerals that precipitate in the sediments. So they're not like classic or sandstone or stuff, they are precipitate minerals. When you look here, we do have the gypsum cases, the fabrics of gypsum in rocks. There's a large number of fabrics, various type of fabrics that are very specific to a specific depositional formation environments. The same kind of fabrics are also seen in the anhydrite sample shown here to the right. Same type of facies, same type of fabrics in the rocks, so they seem to share a common origin. When we look in sections, these sulfates, we see that the gypsum, there's three types of microfacies in the gypsum. We have alabastrine, which is fine-grained gypsum. We have porphyroblastic gypsum, which is coarser grain. And we also have satin spar, which is gypsum present in small fractures connecting various nodules. Of interest is the presence of anhydrite as relics into the gypsum minerals, indicating that originally all this was anhydrite and was later altered into gypsum. There's a lot of different type of microfacies also present in the anhydrite. We just show here a few of those. There are 7 main type of microfacies, largely either fine grain, felted fabric, to coarser grain, prismatic. So different type of fabric compared to the gypsum, but anhydrite, which is important, anhydrite was a primary mineral. When we combine the megafacies, the rock in cores, and the thin sections, all these suggest that the environment of precipitation was what is called a SAPCA, which is an arid, marginal marine environment where high aridity leads to high concentration of minerals in the ground, in the water, and precipitation of the sulfate. So the next point was try to contrast these two types of sulfates using stable isotopes. Sulfur isotope and also oxygen isotope in all these sulfate fabrics. So we analyzed 30 samples, 20 gypsum and 10 anhydrite for their stable isotope composition. But unfortunately, we're still waiting the results, which will of course happen after the election, of course. So before the end of February, we should get the results. The important point is can we contrast these two types of sulfate using their stable isotope signature? And it is very important because of the previous presentation showing that locally we have very anomalous sulfur isotope composition in the dissolved sulfate in groundwater. So this might generate some other ideas about the origin of these. And this is a summary of what is available as information for the stable isotopes of sulfate in southern Ontario. So here we have, what we have here, this is the sulfur, to the right here is the sulfur isotope composition of various sulfate sample in southern Ontario. For the Salina group, we have samples from the Bruce Peninsula and also from some wells in the southernmost part of Ontario. These sulfates do have signatures similar to the normal marine or Silurian signature. Of interest is some sulfate in the Queenston Formation, just north of the area of interest, which have very depleted or light sulfur isotope, which seems to be present in the groundwater, in the sulfate dissolved in groundwater. So this is what we hope to pursue to study and hopefully come with some better conclusions than what has just been shown here. So thank you.